Section 1.1, Linear, Rational, and Absolute Value Equations. We'll start with our focus on linear equations. Before we get started, remember that an equation is an algebraic expression that has an equal sign. When we talk about solutions or roots to the equations, we are talking about values that satisfy the equation. That is, that we can plug them in and we get a true statement. Our equal sign essentially balances. We can also look at linear equations in one variable. A linear equation in one variable is of the form, one second. A linear equation in one variable is of the form ax plus b equals 0. A and b are real numbers, and a cannot be 0. That is, the only variable we have is x. When we go to solve linear equations, there's a variety of properties that we use. You can find those on page 80, but they are the addition property of equality, the subtraction property of equality, the multiplication property of equality, and the division property of equality. What these essentially say is what we do to one side of the equation, we must do to the other. That is, if we divide one side of the equation by 2, we must divide the other side of the equation by 2. Let's now look at a couple examples. So if we want to use these properties of equality, let's solve (5 times 3x minus 2), and it's equal to 5 minus 7 times the quantity x minus 1. We'll start by distributing. That is, we're going to multiply 5 by 3x and 5 by negative 2. So 5 times 3x minus 5 times 2 is equal to 5, and now we'll distribute again. So negative 7 times x is negative 7x, and negative 7 times negative 1 is positive 7, so plus 7. Okay, now we can multiply things out. 5 times 3x is 15x. 5 times 2 is 10. And I'm going to combine some like terms. So 5 plus 7 is 12. And then we'll still subtract 7x. Anytime we're solving a linear equation in one variable, our goal is to isolate x. That is, we want to move all of our terms with x to one side and all of our constants to the other. In this case, we can use the addition property of equality to add 7x to each side. 15x plus 7x is 22x. That minus 10 is still hanging out, and it's equal to 12. To finish isolating x, we will add 10 to each side. Again, we're using that addition property of equality. We have 22x is equal to 22. And if we want to isolate x, we'll divide each side by 22. And we get x equals 1. It's not a bad idea to go back and check. So in order to check, what we would do is substitute our value of x equals 1 into our original equation. And what we would hope would happen is that we'd have both sides of the equation equal to the same number. So in this example, when we divided each side by 22, we were using the division property of equality. You can see that subtraction and multiplication properties of equality will act in a similar way. What we do to one side, we will do to the other. For this next example, we will begin looking at what classifies an equation as an identity, a conditional, or an inconsistent equation. We'll begin with looking at the identities. With an identity equation, it's an equation that is true for essentially any real number for which the equation is defined. Examples that we see include x equals x, or 2x minus 1 is equal to x minus 6 plus x plus 5. If you'll see on this second example, if we simplify the right-hand side of the equation, we get 2x minus 1. I apologize, my puppies are playing. That's what the squeaking is. Other examples include things like x over x equals 1. This is an identity, even though it's not true for all real numbers, but it is true for the set of all x, except when x is 0. This is what we mean. X equals 0 is not included because we can't divide by 0, but all other real numbers would make this equation true. Conditional equations are equations that are satisfied by at least one real number, but they cannot be identities. They may have more than one real solution, such as quadratics. Examples of conditional equations include things like 3x minus 6 equals 12. The reason that this is a conditional is if we use our properties of equality, we can add 6 to each side, and we'd get 3x equals 18. We can divide each side by 3, and we get a specific value for x, particularly 6. Examples where we'd have more than one real solution include quadratics. Think about things like x squared plus 5x plus 6 equals 0. This is a quadratic equation we could factor into x plus 3 times x plus 2. If it's equal to 0, then either x plus 3 equals 0 or x plus 2 would equal 0. And here we would get x equals negative 3 or x equals negative 2. The last type of an equation that we have is an inconsistent equation. These are equations that have no solutions. For example, if we looked at something like 3x plus 9 and it was equal to 3x plus 11. If we went to solve this, we would start by subtracting 3x from each side, and we would have 9 equals 11, which we know is not true. This is what happens when we have an inconsistent equation. We get some statement that is false. Maybe 9 equals 11, it may be 0 equals 8. Other examples, and these may seem silly, but if we looked at 2x minus 2x plus 4 equals 0, this is like saying 4 equals 0, which again we know is not true. Before we move on, I would like us to look at another example and try to classify this equation. So I would like for us to decide if it's an identity, a conditional equation, or an inconsistent equation. So we are going to classify x times x minus 1 minus 6 equals x minus 3 times x plus 2. If you would like to pause and try and do this on your own and then check, you're welcome to do so. We will start by distributing. So when we do that, we're going to look at distributing this x to each of these terms. So we'd have x squared minus x minus 6. And now we want to think about foiling on the right-hand side of the equation, right here. So we'll take x times x, and then that gives us our x squared. When we look at x times 2, that's 2x, and then we have plus a negative 3 times x, so 2x minus 3x is negative x, and then negative 3 times 2 is negative 6. Notice that this is where we have exactly the same thing on either side of the equation, which makes this an identity. If you were to continue trying to isolate x, you would see that 0 equals 0. So with identities, again, you will always see something that is true. Now that we've solved some basic equations, let's look at some equations that involve some rational expressions or some fractions. Don't panic. So, as we begin looking at some equations with rational expressions, we'll begin with this specific example. 2 over x minus 3 minus 3 over x plus 3 is equal to 4 over x squared minus 9. So to begin, we'll start by factoring the denominator. That's the bottom. And the reason that we want to do that is we want to find the LCD. If we factor the denominator, we can't do anything on the left side of the equation. So I'm just going to copy those down. But if we look at the right side of the equation, x squared minus 9 is a difference of squares. So it factors into x minus 3 times x plus 3. So our LCD here, our least common denominator, we find by looking at each of the factors and picking the powers that are needed. All of these are to the first power. And our LCD should just be x minus 3 times x plus 3. Now, in order to work with this, we can start thinking about each of these pieces. If we look at the left side of the equation, the first term, 2 over x minus 3. In order for that to have our LCD, we need this x plus 3 still. We can't just put an x plus 3 in the denominator and call it good. What we need to do is multiply cleverly by 1. So we'll multiply both the numerator and the denominator by x plus 3. Now we'll have that least common denominator and we can distribute still. If you look at the second term in this equation, what we need to do is pretty much the same thing, except we're missing the x minus 3 piece. So we'll multiply by x minus 3 over x minus 3. Okay, so far so good. So now let's distribute. 2 times x is 2x. And then plus 2 times 3, which is 6, over this x plus 3 times x minus 3. And then minus this quantity we're going to distribute here, 3 times x and then 3 times negative 3. So we'd have 3x minus 9 over this x plus 3 times x minus 3. And it's equal to 4 over x minus 3 times x plus 3. Okay, this is one way that we could work with it. Now that we have the same denominator, we could really look at when the numerators are equal, because if we multiply each side by x plus 3 times x minus 3, we'd clear all of our fractions. Okay, as we continue to work on this, I'm going to move this up just a little bit so we can keep working. And what we're going to do is we're going to work on subtracting out this entire term. Now this is one place where people tend to make mistakes. We have 2x plus 6 minus, and now we want to make sure we put the entire second term's numerator in parentheses so we can distribute that negative. And we'll look at another way to approach this one in a minute. Okay, now that we can see that we have to distribute the negative, we have 2x plus 6 minus 3x. And then when we take a negative 9, that's plus 9 over our LCD is equal to 4 over our LCD. Okay, and again, the reason that we can now just look at when our numerators are equal is because if we cleared the fractions we'd multiply each side of the equation by the LCD, making use of that multiplication property of equality. And notice the LCDs would reduce to 1. So we would be left with, when does, when does 2x plus 6 minus 3x plus 9, when does this equal 4? Combining like terms, we'd have negative x plus 15 equals 4. Subtract 15 from each side. Negative x is equal to negative 11. If you divide each side or multiply each side by 1, we'd get x equals 11. Now, the only thing we should do at the end is we should go back and make sure that this is not a particular value that would make a denominator 0. In this case, it doesn't, so this should be our solution. Again, if we wanted to check, we would go back and plug it into the original equation and make sure that we had two equivalent expressions. An alternate way to solve this equation would be to find the LCD, which again means we'd need to factor. Since this is the same problem, it should factor in the same way as we start. So it's equal to 4 over this quantity x plus 3 times x minus 3. The LCD is still x plus 3 times x minus 3. Now with this approach, and this is one that I sort of like to use a lot, is we'd multiply each side of our equation by the LCD. And this would allow us to clear the fractions. So we're going to multiply each side of the equation by x plus 3 times x minus 3. Notice when we do that, we'll have to distribute on the left side. So as we distribute, we have x plus 3 times x minus 3 times our first term, 2 over x minus 3, minus, x plus 3 times x minus 3 times our second term, which we said was 3 over x plus 3. And it's equal to 4 over this x plus 3 times x minus 3 times x plus 3 times x minus 3. Now, here's the beautiful thing. We can think of each of these as being over 1 if we would like, which helps us think a little bit more about fractions. Now we can look for terms that reduce. X minus 3 over x minus 3, those reduce to 1. Over here we had an x plus 3 and another x plus 3, those reduce to 1. And notice on the right side of the equation that these all reduce to 1. So now we're looking at a much simpler expression. 2 times x plus 3 minus x minus 3 times 3 should be equal to 4. Now if we distribute, we'd have 2x plus 6, and then I'm going to think of this 3 as being right here, not that it matters, but I've got a negative 3x, and then a positive 9 is equal to 4. So we get negative x plus 15 equals 4. Again, isolating x. Negative x is equal to negative 11, which means when we divide each side by negative 1, we get x is equal to 11. This is exactly the same thing we had last time. If in fact at the end we had gotten x equals 3 or negative 3, these would be what we call extraneous solutions, because as we put them in, we'd be dividing by 0, which is impossible, and our solution would be the empty set. Equations with absolute value. If you remember the absolute value, you may be familiar with something like the absolute value of x, which is the function that allows us to take values and make them positive. This is because the absolute value function tells us how far away from 0 a number is. And distances, as we know, are always positive. We never say we're going to go negative 2 feet because we wouldn't know if that would mean we'd go back 2 feet or for some reason would have to go 2 feet into the ground. Okay, so distance is always a positive value. As we begin solving some equations with absolute value, we'll work through the process. So I would like for us to solve something like the absolute value of 2x minus 3 is equal to 5. In this, we would expect two solutions because it's possible that 2x minus 3 equals 5, or that 2x minus 3 is really the same as negative 5, because when we take the absolute value, it would be positive 5. So, in order to do this, we are going to set 2x minus 3 equal to 5, and we are also going to set it equal to negative 5. We're solving two different equations, but you'll see the steps are the same. So we add 3 to each side in our goal to isolate x. We'd get 2x equals 8, or 2x equals negative 5 plus 3, which is negative 2. And now to finish isolating x, what we need to do is divide. So divide each side by 2. And on this first equation, we get x equals 4. Or on the second equation, we get x equals negative 1. Here we have two solutions. This is a conditional. Let's go back and check, because I think some of you may feel skeptical. Okay, if we look at 2 times 4 and then subtract 3, we want to know, is that equal to 5? Well, is 8 minus 3 equal to 5 in absolute value? The absolute value of 5 is in fact equal to 5. We feel pretty pleased with that one. Now let's check the other one. Let's check negative 1. So we'd have 2 times negative 1 minus 3 in absolute value. We want to know, does that equal 5? Well, negative 2 minus 3 is in fact negative 5. So as we look at this, we would have the absolute value of negative 5, which is in fact equal to 5. So you can see that we have two solutions. This concludes section 1.1. We will work on applications or discuss some applications during class. I hope you learned a lot and took some good notes, and I'll see you soon.